Our learning goal for today is I am able to draw the electric field vector at any location around charged particles. So before we talk about that learning goal, let's talk about something we learned last year, and that is gravitational fields. So we can say the Earth produces a gravitational field, and that gravitational field points towards it. Meaning, if I were to take any object, for example, the moon, and I were to place it within this gravitational field, the moon would experience a force. Now, what's the size of this force? Last year we learned, well, the force of gravity between any two objects is this gravitational constant times one of the masses, for example, the Earth, times the second mass, which is the moon, divided by the distance squared between them. We've learned in this course so far that if I have a positive charge and a negative charge, those two will exert a force on each other. And Coulomb's law says the size of that force depends on the size of the two charges, how much charge each has, and the distance between them. So similar to thinking about gravitational fields, we can say this charged particle also produces instead of a gravitational field, an electric field. Meaning, if I were to put a positive charge there, well, it's going to move towards it. So I can visualize an electric field. And this electric field is going to tell me the direction of the force if I put a charged object inside or near that field. Okay, now, last year, when we talked about force of gravity, we used this formula a lot last year. Fg is mass times gravity. What we did is this g, this gravitational constant right here, which for Earth was 9.8, that was, if you take the mass of the Earth and the distance, which is the distance from the center of Earth to the surface, this is all, if we multiply these three numbers together, we get roughly 9.8. So I'm just going to rewrite this. The mass 2 is exactly the same as before. And now instead of writing g m1 and r squared, we wrote this last year. We can do the exact same for electric charges. So let's say this is charge 1. And this is charge 2. The force, well, we can say that this charge produces an electric field. That electric field is going to be this size. So notice, as the distance goes farther and farther away, the electric field is going to get smaller and smaller. So, and the force on a charged object placed inside that electric field would be its charge times that electric field. So we can see the similarities between gravity and electric charges. So our general formula that we're going to use for the rest of today, the rest of the year, is if I want to know the force on a charged object, well, I need to know, one, the charged object that's placed within the electric field. Let's look at an example. Where would a positive charge go? Okay, if I were to place a positive charge here, which direction will it go? Well, it will go away. So when drawing electric field lines, which tell us the direction of the electric field, you want to ask yourself, where would a positive charge go? And that's going to be the direction of the arrows. Whereas in this case, where would a charge, if I put a positive charge here, it would move towards this object. Or if I put a positive charge here, for example, it would move towards this negatively charged object. So the direction of the arrows, if you're trying to figure out which direction the electric field is, just ask yourself, where would a positive charge go? So let's see what this looks like. So here, I have a positive charge, and this positive charge creates an electric field around it. Notice if I move the charge, the field is also changed. Now this is, if I want to know which direction the arrows go, you ask yourself, where would a positive charge go? Where would a positive charge go if placed around this object? Well, it would go away. If I change this instead to a negative charge, we've got a positive charge would get sucked in towards it. So in terms of figuring out the direction, just think of that. Where would a positive charge go? Now, as we get farther and farther away, you can imagine the electric field is going to get smaller and smaller and smaller. So this question says, draw the electric field vector at the 3 points. Okay, the vector it's talking about, that would be the direction at this point. For example, we have two charges here, and we want to find which direction would a positive charge go when placed here. Okay, well, what we can do is figure out each one individually. So let's ignore this charge for now and just look at this charge and say, okay, if I were to put a positive charge here, the electric field that would be created from this charge would be in this direction. Okay, now how about from this charge? The electric field that would be created here from this charge would be in this direction. So if I were to add up those two vectors, I would get this vector. So this would be the direction of the electric field at that location. Let's try it with these two. Positive, it would get pushed away. Positive would get pushed away. Since they're equal distance, my electric field is 0 at this point. How about this last point? Positive gets pushed away. Positive, not quite, not close, but it'll still have an effect. So if I add up those two vectors, this is going to be my electric field. So let's see if we can visualize this with our simulation. Here's one positive charge. Here's another positive charge. Which way would it go? It's going to get pushed away. You can see what happens to the vectors. One last question. Compare the electric field strength E1 and E2 at the 2 points labeled 1 and 2. For each, is E1 greater than E2, E1 equal to, or less than? So the first we need to do is we want to figure out the electric field strength. So let's figure out what the electric field looks like at these points. So from this charge, the electric field is in this direction. From this charge, the electric field is in this direction. So notice these two would cancel each other, and I would get an electric field of 0. At 2, well, this would push away. This one would also push away. So my net electric field vector is going to be to the right. So for this case, E2 is larger than E1. That's it. Try the rest of the problems yourself.